Welcome to the Explainer. So today is June 30, 2026, and literally, as we speak, high above our heads, NASA is pulling off one of the most unprecedented, daring robotic missions in history. We're talking about a high-stakes orbital heist to save a dying space telescope before it completely burns up in Earth's atmosphere.
6 months. That is exactly how much time is left on the clock. If nothing happens in the next half year, this absolutely invaluable piece of technology faces a fiery, completely uncontrolled re-entry. The clock is ticking, fast. Which brings us to the monumental question. How do you save a $250 million space telescope that is, quite literally, falling out of the sky? Okay, let's dive right into this. Because this isn't just about saving some metal and glass, right? It's a high-speed race against time, physics, and the extreme environment of low Earth orbit.
Section 1. The Taking Orbital Clock.
You know, every great heist needs a formidable antagonist, and ours happens to be atmospheric drag. See, even when you're hanging out 400 to 600 kilometers up in space, where you'd think it's a total vacuum, there are actually just enough stray particles from Earth's upper atmosphere to create this relentless drag force. It's this slow-moving, invisible threat that's constantly acting on all low Earth orbit satellites, just steadily sapping away their orbital energy. And Swift's sudden drop? It's pretty staggering. It was originally placed in a nice, safe 600-kilometer orbit back in 2004, and the plan was for it to stay up there for decades. But, well, our sun had other plans. We recently got hit by an unprecedented peak in the solar maximum. All that intense solar radiation violently heated the Earth's upper atmosphere, causing it to puff up and expand. All of a sudden, Swift was plowing through a much denser layer of gas, which completely dragged its orbit down to just 360 kilometers. And that happened in a mere 2 years instead of decades. Crazy, right?
Section 2. A priceless scientific legacy.
So why go through all this trouble? Well, the Neil Gehrels Swift Observatory is an absolute marvel. Over its 22-year legacy, it's detected over 1,700 gamma-ray bursts. We're talking about the most powerful explosions in the entire universe here. It's observed light from more than 13 billion light-years away. But here's the kicker. It is the only observatory capable of simultaneous gamma-ray, X-ray, and optical observation. Literally, not even the mighty James Webb or Hubble telescopes can react to gamma-ray bursts in real time the way Swift does. Oh, and it even gave us the first direct observation of a neutron-star collision. That's how we proved where heavy elements, like the gold and platinum in your jewelry, actually come from. But beyond that staggering scientific value, there's a very grounded, practical, economic reality at play here. Dr. Brad Senko, the principal investigator for Swift, openly admitted that, sure, they could just build a new one, but the cost difference is massive. So, the crucial point is this. Letting Swift burn up means losing a totally irreplaceable asset for observing the universe. And replacing it the traditional way, that is a massive financial and temporal hurdle.
Section 3. The $30 million plan.
This massive hurdle is exactly why NASA took a gamble on a small Arizona startup named Catalyst Space. Think about the traditional route for a second. Building a new telescope usually costs around $250 million and takes, 5 to 7 years. But Catalyst Space, they built their rescue spacecraft, which they call Link, in just 8 months. And they did it for only $30 million. If they actually pull this off, it gives Swift 5 to 10 more years of life at just 12% of the cost of building a new one from scratch. But here's the $1 million, or I guess $30 million question. How on earth do you grab a 22-year-old satellite? That is the primary engineering nightmare. See, Swift was never designed for servicing. There are 0 mechanical grapple points on it. Engineers described this perfectly. They said, it's like catching a slippery box with no handles. The 450-kilogram Link spacecraft has to use 3 highly advanced robotic arms to physically grip the telescope's body, all while both of them are zooming through space at roughly 27,000 kilometers per hour. And the way this mission kicks off is incredibly cinematic. Link isn't launching from some concrete pad on the ground. It's using an airborne launch. A legendary 1974 Lockheed L-1071 aircraft named Stargazer carries a Pegasus rocket all the way up to 39,000 feet. Then it just drops the rocket. The rocket free falls for 5 terrifying seconds before the engines ignite, blasting Link into low Earth orbit in under 10 minutes. Honestly, it's incredibly fuel efficient, and it means it can launch from practically anywhere over the ocean.
Section 4. 7 phases of capture. Okay, once they are actually in orbit, the margin for error essentially drops to absolute zero. Let's walk through this ticking clock timeline. The first week is all about this gradual, heavily calculated approach, mostly just to avoid crashing into the thing. But fast forward to day 10, the capture phase. This is the terrifying climax. Link's 3 robotic arms have to perfectly sync up with Swift and grip it simultaneously without doing any damage. A single millimeter of miscalculation right here, that won't just fail the mission, it could literally destroy both spacecraft instantly.
I mean, the team is facing a pretty grim reality with 5 major risks. First, Swift might be tumbling uncontrollably. Second, it's losing up to 100 meters of altitude every single day. Third, as we covered, no standard grapple points. Fourth, there is absolutely zero budget for backup systems. And fifth, one wrong move turns 2 perfectly functioning machines into a massive cloud of hazardous space debris. It is quite literally like trying to build a 1,000-piece puzzle while you're free-falling. Section 5, a $10 billion future.
But if they pull it off, the payoff is massive. And this brilliantly illustrates how saving just one legacy telescope can impact the entire aerospace ecosystem. Think about this. The satellite servicing market is projected to reach an incredible $10 billion by 2030. Refueling makes up about 40% of that, sure, but repair, orbit boosting, and debris cleanup make up a huge chunk too. Swift Boost is basically the ultimate critical test case. If Catalyst succeeds, they prove that space is no longer a graveyard for expensive technology. Instead, it becomes a reusable, service-friendly environment.
Now, Catalyst Space is stepping into an arena with some really major players. You've got aerospace giants like Northrop Grumman pioneering refueling for satellites that actually have standard interfaces. Then you have companies like Astroscale and ClearSpace working on debris removal. But Catalyst really stands out here. Why? Because they're tackling the unique, vastly harder challenge of rescuing legacy satellites that were never ever designed to be serviced in the first place.
So, as we pull all of this together, here are the core takeaways you should remember from this explainer. 1. Startups can absolutely shatter those traditional 5-year aerospace cycles. Catalyst did this in just 8 months. 2. Old legacy satellites are incredibly valuable and they are absolutely worth saving. 3. Going forward, future satellites must be designed with standard attachment points for servicing. But above all, this mission proves a fundamental shift. Space is no longer a one-way trip. Thanks to these public-private partnerships, we can actually go back, return, repair, and reuse. I want to leave you with this final provocative thought. If a 22-year-old tumbling, falling telescope can spark a brand new $10 billion industry and completely rewrite the rules of aerospace engineering, what other impossible space missions are suddenly within our reach? Thank you so much for joining me for this explainer. Keep your eyes on the skies because human ingenuity is really just getting started, and I literally cannot wait to see what we pull off next.